This presentation is a recap of the one that was delivered at the Fraunhofer Institute as part of the Cost Action NEWFOCUS meeting in Berlin in June of 2023. The talk is about optical wireless communications. Actually, the cost meeting, this NEWFOCUS project addresses in general optical wireless communications from short range, medium range, and long range optical wireless communications. So it's very wide in scope. And so that's the main topic of my presentation today, although I'm going to specifically focus on the potential of photonic integrated circuits for advancing optical wireless communications. And now this is the outline of the talk. Obviously, I couldn't start talking about optical wireless communications without mentioning I would say conventional wireless RF communications. And so I will start by, as a short introduction, to present the evolution of, at least in my point of view, of wireless RF communications. And I will argue during the presentation that optical wireless communication is going through a similar evolution. Okay, and then I will address the main topic of the talk, which is the photonic integrated circuit technology, how it can advance or be applied with success in optical wireless communications. Obviously, in photonic integrated circuits are integrated. Basically, the light signal is propagated within a waveguide, and so we need some means to transfer the signal from the waveguide to free space for optical wireless communications, and that's where I will start by addressing how this can be done. And specifically, I will focus on optical beam steering and optical beamforming, and finally, some applications of this technology and the conclusions. And so, as I said, there's a motivation as introduction to wireless communications. As you probably are all aware, wireless communications has rapidly evolved to meet increasing demands for higher data rates, improved coverage, and lower latency in many different types of applications. And in 6G, there's even a higher need for advanced technologies to support new emerging applications and services. In this scenario, the demand for high-quality video streaming is very important. There are many applications like augmented reality, virtual reality, and Internet of Things. There are a myriad of applications which has fueled the need for faster and more efficient wireless communications. And if we look at this plot here on the right, we see that mobile services data rates are predicted to be comparable to wireless local area networks by 2035, which shows the increased importance of these mobile services and wireless communications in general. Some research directions with the objective of increasing data rates. Either we move to increase the spectral efficiency, which is in general difficult to implement and costly. Another solution is to explore higher frequency bands or larger bandwidth, moving to, for example, sub-terahertz and terahertz bands. 6G is addressing this challenging of moving to sub-terahertz bands. There's already a standard being assigned, 802.15.3D, where the frequency bands between 250 and 320 gigahertz have already been assigned for wireless communications, which shows the increasing importance of wireless communications and sub-terahertz and even terahertz bands for wireless communications. In terms of evolution of wireless communications, conventional RF technology, we've seen a move from legacy systems that used sector antennas serving a wide range of users, moving to MIMO using multiple beams. Okay. In that sense, MIMO or massive MIMO is already being implemented in 5G. There are already different suppliers of this technology, so it's not really a new area of research in itself. But the problem is when we move to higher frequency bands, we have to account that there are additional challenges to overcome, namely atmosphere attenuation, because of at these frequencies the attenuation in the atmosphere is much higher, which means that the link distance becomes shorter. So we are talking about short range communications, and also due to the attenuation also and the reduced signal amplitude or signal power, usually it requires also a line of sight because it will be difficult to go through obstacles, for example. And this question of the non-line of sight problem, curiously, it's been a problem that has been so far associated with optical wireless communications, because in RF, at least lower frequencies, we know that the signal can pass through walls with some attenuation, obviously, that can go through. But as we move to higher frequency bands, this becomes a problem which has conventionally been associated with optical wireless communications, which is very interesting to note. And as we move to higher frequency bands, sub-terahertz bands, and beamforming and beam steering becomes extremely important, mainly in 6G or beyond 6G communications, for increased efficiency, reduce interference, and also to increase the signal quality. Still, terahertz wireless communications, there are still some technological challenges that still need to be overcome, namely the availability of high-power terahertz sources suitable for modulation, beam steering capability, as I mentioned, signal conditioning and processing, high-speed electronics, and also the availability of low-cost and small form factor, which can be produced in large scale, or technology for large scale production. And this in itself is difficult to achieve solely on current RF wireless technologies. I made some point in a paper, actually, the paper that I presented in one of the slides before in a paper that is being published on this one here in ESCTech Science and Society. So and my argument there was that electronics by itself is not sufficient to overcome all these obstacles for terahertz wireless communications, and photonic integrated circuit might be, or hybrid integration of the two technologies might be the way to move forward. But this is not the main point of my presentation today. So I will argue here that this is difficult to achieve all these challenges solely on RF wireless technology. But in terms of MIMO and beamforming, as we've seen, is one of the last stages of the evolution of wireless communications. MIMO in general, they use narrow beams with multiple columns of dipoles spaced to minimize interference, which enables us to have multiple beams either in horizontal or vertical direction. The antenna elements work together to create a high signal gain. And in terms of the way how this works is in general known as a phase array antenna, where traditional this is done by, or beamforming is done by using phase shifters to shift the phase of the signal that's being applied to each element, which enables one to direct the beam to specific directions. Okay, just a little overview of this, or a background on this technology of beam steering and beamforming. If we have a set of identical isotropic radiators, if they all have, and the signal applied to each one is the same, so the wave that is generated by each element is in phase, which means that there is constructive interference on the plane perpendicular to the elements. And so to achieve constructive interference in a different direction, we should control actually not the phase, but the delay, although traditional, this is done by adjusting the phase. Because at one frequency, if we are using very narrow, or the signal with a very narrow bandwidth, at one specific frequency, controlling the delay is equivalent to controlling the phase. And so controlling the phase, as is been traditionally done, works for narrowband signals. And so if we change the delay of the signal applied to each element, we can provide constructive interference in a different direction. And this is how antenna phase arrays works in wireless communications, RF wireless communications. Now moving on to the role of optical wireless communications. The idea is that optical wireless communications can complement RF communications and answering the evolution of the wireless communications and needs for CG, and satisfying the needs or these requirements that I've discussed before of higher data rates, low latency. And in fact, when we are talking about optical wireless communications, in fact, we are moving to even higher frequency bands, so hundreds of terahertz, where the available bandwidth is much higher. And so I would say that there is an important aspect of optical wireless communications is the available bandwidth and the data rates available at this band. And so the role will be to overcome the current limitations, addressing these challenges like limited bandwidth, interference, and security vulnerabilities. It can potentially provide improved performance, scalability, and energy efficiency, and in this sense, meeting the requirements of emerging applications and future wireless communications. Now, if we look at evolution of, in a very short slide, of optical wireless communications, the first systems use light emitting diodes with wide beams, and so far until now, I had addressed this technology as optical wireless communications, OWC, although sometimes there's another term that is known in the literature, which is Li-Fi, light fidelity, in the sense similar to the wireless fidelity systems. And so I'm going to use here these two designations interchangeably, so either one or the other, but meaning exactly the same. Although sometimes in the literature, some authors refer to this in not exactly the same technology, well, as if optical wireless communications is a general, more wide scope technology, where Li-Fi sometimes is referred to as specific applications of optical wireless communications. I'm not going to make any distinction here between the two. But what I want to stress here is let's say the first systems of Li-Fi use light emitting diodes with wide beams. And so here you see an analogy with the first wireless communication systems that used wide cells. Now the following systems use multiple LEDs with lenses, which are identical to MIMO. And now I think the next step will be the use of narrow beams, which will be identical to beam steering and beamforming in advanced RF wireless communications, which I would call this as Li-Fi 2.0. And so we see here a similar evolution of optical wireless communication with respect to RF technology. And I think that's what I'm going to argue next, is that photonic integrated circuits can provide some means to enable us to move forward to this Li-Fi 2.0. In terms of the technology of photonic integrated circuits, it can provide very high integration level at the transmitter and receiver, increase data rates, capacity through advanced modulation techniques, improve beamforming and beam steering for enhanced coverage. Potentially, it can provide compact size and high integration density, reducing footprint and increased component density, reduce power consumption with respect to electronic counterpart technology and heat dissipation, improve reliability and functionality, and also the potential for cost-effective mass production and cost-effective deployment and scalability. And I will now have a few slides on silicon photonic integrated circuit technology itself, in a short introduction to the technology itself. It has so far been already proved to be relevant in wired communications, in optical communication, for example, by enabling the development of very high speed transmitters and receiver with compact size, low weight, and reliability. The technology itself has been forecast, or silicon photonic dyes, in terms of future application. It is forecast that photonics-based transceivers will witness a compound annual growth rate of 36%, which is quite relevant. There are here basically two competing technologies in photonic integrated circuit. silicon photonics, as I mentioned before, and also indium phosphide technology. We see here that silicon photonics is increasing in terms of number of components per PIC, is increasing at much higher rate than in the indium phosphide. Although I see that the heterogeneous or hybrid systems that use both technologies, silicon and indium phosphide, is very attractive. Because, as I didn't mention, but indium phosphide enables one to integrate active devices, namely laser diodes and LEDs integrated on the chip, where silicon photonics does not enable one to have these sources, light sources within the chip. And so the integration of the two technologies is quite interesting. I'm going now to address some of the, let's say, the state of the art of technology, just to mention that nowadays the silicon photonics technology has already achieved a maturity equivalent, let's say, to circuit design, where many foundries provide a process design kit, which includes a library of components for circuit design, instructions for laying out the chip, a design rule check, and so there's also simulation layout and rule check that enables one to design and check the integrity of the chip before sending to fabrication. Okay, this is a diagram of a typical chip structure, defined in terms of GDS description layers, which involves the optical waveguides, silicon modulators, detectors, and also layers for metal layers and vias to connect the different layers. And so these are, let's say, basic components. Obviously, there are many other components that you can integrate on the chip. These are some of the basic ones. In terms of design, there is the design may involve several steps, going through numerical simulation of the optical components, which is possible to do through availability of some specific simulation software, which involves solving the Maxwell equations, and after that, functional models can be derived, which are in turn used for simulation at the system level. Some of the simulation software that is available is Numerical. Numerical is now sold by ANSYS, and Synopsys has also simulation software and layout software for photonic integrated circuit design. This is a diagram of a typical transceiver that involves several components: waveguides, direction couplers, Y branches, modulators, grating couple to couple the signal from the outside to the inside the chip, photodetectors. There's some metal connections to the device, some electrical pads for applying the signal, for example, RF signal. All these integrated on the chip. This is a typical waveguide, which is silicon on silica waveguide. So it's a silicon waveguide surrounded by silica or glass. It provides a good way to coupling to optical fibers and has a low loss of about 3 dB per centimeter. Recently, or more recently, it has around for many years now, but there's an alternative technology which is based on silicon nitride, IMEC, for example, which is a foundry, developed a low-pressure chemical vapor deposition process, which has inherently low loss, a few dB per meter, so less attenuation than the silicon one, with a resolution of less than 1 nanometer on a 200 millimeter wafer. With a very high power handling in the watt range, and also wide wavelength from 400 nanometers to 2500 nanometers. And you see that within this very wide range, it includes standard infrared wavelengths used in telecommunications, but they also can also be operated in the visible region. As this is also very interesting because some of the Li-Fi systems, they use visible light communication instead of infrared. In terms of the simulation, you can simulate the propagation of the optical mode in the waveguide, obtain some important parameters as the effective refractive index of the mode, and the complete profile of the refractive index. The bands within the chip are an important part. You have to direct the beam to the place where you want to, but whenever there's a band, there's the mode is shifted to slightly to the outside of the waveguide, which increases the losses, so that there's an additional loss when you have a band. And so that's why the curvature usually is limited to some values to not to reduce the loss when you have a curvature. This is from the model you can extract by the simulation at optical propagation. You can extract S parameters of a device, which can then be integrated on a higher level simulation. In terms of modulation, one important device is the Mach-Z interferometer. Basically, the Mach-Z interferometer is this scheme shown here, where you have the light signal, which is split between two branches, and then is combined later at the end, and this provides an interferometer. If we are able to modulate the phase of the signal in one of the branches, we can change the amplitude of the signal at the output. For example, basically we have ideally two identical signals traveling in each branch. If, for example, we have a 180 degrees phase shift, then the signals are out of phase when they combine, and so we have a total of distracted interference, a cancellation of the signal, and this can be used, for example, for on-off modulation, which is the simplest, for example, modulation that we can obtain for optical communications, for example. An unbalanced Mach-Z interferometer. With this device, we see that the output of the interferometer is a sinusoidally varying function of wavelength, which provides tunability of the device and can be used to implement high-speed Mach-Z modulator, for example. and here we have the capability of tuning the device to a specific wavelength, and it has many other applications. Okay. So by changing the difference in length between the two branches, we can change the, let's say, the frequency response of the device. Interesting enough, I think this is a very clever way of doing the modulation on the phase modulation, which is so here basically at the middle of this diagram here, you have the waveguide where the wave is going through the waveguide, And then you, within the waveguide, you provide a PN junction. And by changing the voltage applied to the PN junction, you change the depletion region within the waveguide, and which means that the number of carriers within the waveguide changes with applied voltage. And through the plasma effect, this leads to a change in the refractive index. And so the change in the refractive index changes the phase of the signal that's going through the waveguide. And in this way, you can, by applying a signal or voltage, you can change the phase and provide, in this case, modulations through this process. Here you see by changing the voltage, you increase the depletion region, which changes the number of carriers in the waveguide. And the question that raises, and that you probably are thinking, that I also mentioned at the beginning of the talk, which is, here we have photonic integrated circuit where the signal is going through a waveguide, but then how can we use this technology for optical wireless? So we need some means to transfer the signal from the waveguide to free space. And one of the means to do this is to use a waveguide grating, which basically is a diffraction grating which couples light from the chip to free space. And here we see a basic diagram where we see the optical signal going through the waveguide, but on top of the waveguide we have this diffraction grating, which diffracts the optical power, which is coupled to free space. Okay, the direction to where the beam is actually diffracted to is given by this equation here, which depends on the effective refractive index of the material, and also the period spacing of the grating, but also on the incident wavelength, which means that if we change the incident wavelength, we are able to change the direction of the beam. And so by providing some tunability of the wavelength, we can achieve tunability on the diffracted beam or the direction of the beam. And this is one of the techniques that can be used, for example, to provide beam steering of the beam by changing the wavelength of the incident light. But this only provides tunability in one direction, in the direction parallel to the diffraction grating. If we want to achieve tuning in the transversal direction, we can use multiple channel gratings where we apply a phase shift, a phase difference that is applied, of the signal applied to each element, which can provide, in this instance, tunability in the transversal direction. And this is a previous result that is being published in a paper in 2019, where they achieved a wide beam steering range of 45 degrees in the transversal direction, where the phase shift is actually provided like using the similar technique that I showed you before for the interferometer Mach-Zehnder modulator, by providing a PN junction, and by applying a voltage in the junction, the plasma effect changes the refractive index, which changes the phase of the signal going through to each element. As an example, this is a result where they use 16 channel gratings, optical phase array, with a beam steering capability of 20 degrees by 14 degrees. In this case, the the tunability in the longitudinal direction is provided by the change in the wavelength, which has a sensitivity of 0.14 degrees per nanometer. And so within this wavelength range, which is about 100 nanometers, you have the mentioned 14 degrees of beam steering in this device. This is just a slide to show you that by providing a phase change to each channel grating, you can actually provide tune the direction of the beam in the transversal direction. This is another example where they achieved a 46 by 20 by 10 degrees in the transversal and longitudinal direction, respectively, with a beam diversion of around 0.7 or 0.9 degrees in each of these directions, using the same technology. Now I have a slide here that shows one of the main applications of optical wireless communications, which is in Industry 4.0, which is a standard which involves the advanced automation of manufacturing processes. And optical wireless communications is well positioning here to meet these industry requirements by reducing electromagnetic interference, which is very challenging in industry scenarios, reduce channel interference, and is able to provide low latency and fast communications. And usually low latency is very important, for example, for controlling robots, for example, that are doing some critical operations. Beam steering can be used for direct line of sight by providing low latency, as I mentioned, reduced complexity of the signal detection, which is important for critical operations. Beam steering, which requires direct line of sight, obviously, if we are tracking a robot that is moving in the manufacturing scenario, there must be some means of localization of the robot as it travels around the factory. So we can direct the beam to the device as it moves around. And so there's another challenge in here to apply this beam steering capability in this scenario, which is also localization, which might involve, for example, cameras to aid the localization of the devices, or some other means to achieve this. I will finish by saying that optical wireless communications, as I said, or Li-Fi, is very attractive as we move to a higher frequency bands, and as the spectrum gap between RF and optical is shrinking. In my view, this is a great opportunity for optical wireless communications, which so far has been lagging behind conventional RF optical communications. I just have a slide here this plot on the right, which shows that infrared beam steer outperforms 802.11 systems by far, and so I think we have here an important niche of application for optical wireless communication as we move to higher frequencies, and also these very challenging applications such as Industry 4.0. And so The final slide with conclusion is that optical beam steering is a natural evolution to optical wireless communications, which I called in a previous slide Li-Fi 2.0, I try to argue and make a point that photonic integrated circuit technology can provide a scalable and energy efficient solution for Li-Fi 2.0, and which hopefully ultimately lead to the conversion of RF and optical wireless systems. Thank you.
Thank you.